Today, we're going to talk about order of reactions.
Order, 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 order.
Determining reaction orders. With the initial rate in hand, we can determine reaction orders. Let's first discuss what reaction orders are and then see how to determine them by controlling reactant concentrations. First, second, and zero orders. A reaction has an individual order with respect to or in each reactant and an overall order, the sum of the individual orders. Consider first the simplest case, a reaction with only one reactant, A, two products. First order, if the rate doubles when concentration of A doubles, the rate depends on A raised to the first power. Thus, the reaction is first order in or with respect to A and first order overall. Rate is as follows. Second order, if the rate quadruples when concentration of A doubles, the rate depends on A squared. In this case, the reaction is second order in A and second order overall. Rate is as follows. Zero order, if the rate does not change when concentration of A doubles, the rate does not depend on concentration of A, but we express this fact mathematically by saying the rate depends on concentration of A raised to the zero power. That the reaction is zero order in A and zero order overall. For a general first order reaction, the rate is the negative of the change in concentration of A divided by the change in time. Rate equals negative change in concentration of A over change in time. It can also be expressed in terms of the rate law. Rate equals K times concentration of A. Setting these two expressions equal to each other gives, through the methods of calculus, we integrate over time to obtain the integrated rate law for a first order reaction. For a general second order reaction involving two reactants, A and B, the expression including time is complex. In the simpler case, the rate law contains only reactant A. Setting the two rate expressions equal to each other gives integrating over time gives the integrated rate law for a second order reaction involving one reactant. Therefore, the equation is as shown. 1 all over concentration of A subscript E minus 1 all over concentration of A naught equals K times time for second order reaction, along with its rate. For a general zero order reaction, setting the two rate expressions equal to each other gives integrating over time gives the integrated rate law for a zero order reaction. Concentration of A subscript T minus concentration of A naught equals negative K T. Zero order reaction and rate equals K. Concentration of A raised to 0 equals K. We first found the reaction orders using rate data. If rate data are not available, we arrange integrated rate law into an equation for a straight line, y equals mx plus b, where m is the slope and b is the y-axis intercept. We then use a graphical method to find the order. For a first order reaction, we have natural logarithm concentration of A naught over concentration of A subscript T equals KT. We know that natural logarithm a over b equals natural logarithm a minus natural logarithm b. So we have natural logarithm a naught minus natural logarithm a subscript t equals kt. Rearranging gives natural logarithm concentration of a subscript t equals negative kt plus natural logarithm concentration of a naught. Therefore, a plot of Ln concentration of a subscript t versus t gives a straight line with slope equals negative k and y-intercept equals natural logarithm concentration of a naught. For a second order reaction with one reactant, we have 1 over concentration of a subscript t minus 1 over concentration of a naught equals kt. Rearranging gives 1 over concentration of a subscript t equals kt plus 1 over concentration of a naught. In this case, a plot of 1 over concentration of a subscript t versus t gives a straight line with slope equals k and y-intercept equals 1 over concentration of a naught. For a zero-order reaction, we have concentration of a subscript t minus concentration of a naught equals negative kt. For rearranging gives concentration of a subscript t equals negative kt plus concentration of a naught. A plot of concentration of a subscript t versus t gives a straight line with slope equals negative k and y-intercept equals a naught. Now, what we need to remember. An experimentally determined rate law shows how the rate of a reaction depends on concentration. Considering only initial rates, that is, no products, the expression for a general rate law is rate equals k times concentration of A raised to m times concentration of B raised to n. This reaction is mth order with respect to A and nth order with respect to B. The overall reaction order is m plus n. Next, with an accurate method for obtaining initial rates, reaction orders are determined experimentally by varying the concentration of one reactant at a time to see its effect on the rate. By substituting the known rate, concentrations, and reaction orders into the rate law, we solve for the rate constant k. Integrated rate laws are used to find either the time needed to reach a certain concentration of reactant or the concentration present after a given time. Arrangements of the integrated rate laws that give equations in the form of straight line allow us to determine reaction orders and rate constants graphically. Some trial and error graphical plotting is required to find the reaction order from the concentration and time data. If you obtain a straight line when you plot natural logarithm concentration of reactant versus time, the reaction is first order with respect to that reactant. If you obtain a straight line when you plot 1 over concentration of reactant versus t, the reaction is second order with respect to that reactant. If you obtain a straight line when you plot concentration of reactant versus t, the reaction is zero order with respect to that reactant. Now, an overview of zero order, first order, and simple second order reactions is shown.